Three things that we're going to be covering. One is the naming, making sure you guys can look at a compound like what you did in lab, and then name them or write the formula. The second is to recognize something called isomers. That is, they might have the same formula, but they are actually different compounds. You need to be able to recognize that. And then the last is called crystal field theory. And you guys should, the background to understand crystal field theory comes from Chemistry 200, where you guys studied valence bond theory and molecular orbital theory. So it covers that aspect. Anyway, let me get started here on some of the fundamentals. Okay. So some of the fundamentals is that the metals that we are going to be looking at are going to be transition metals for the most part, maybe lanthanide, actinide metals, but transition metals for the most part. Why transition metals? Because they have d orbitals. And the d orbitals allow a chemical with lone pair electrons to bind to these metals. The metals are going to be the center site. The ligands with lone pair electrons are called, the chemicals with lone pair electrons are called ligands. Okay, L-I-G-A-N-D, ligands. Some people call it ligands. I learned it as ligands. Okay, so it depends on whether you're across the pond and they say ligands, but here in the West Coast we call it ligands. Anyway, these ligands, just like what were some ligands that you guys are used to? Ethylene diamine, that's a ligand. Ammonia, that's a ligand. Water is a ligand because it's got lone pair electrons that can bind to the metal. So we're looking at Lewis acids and Lewis base. Remember that from acid-base chemistry? Lewis base are chemicals with lone pair electrons to donate, like ammonia, NH3. Lewis acids are chemicals that will accept lone pair electrons. So that's what we're looking at. And in order for you guys to get accustomed to some of the vocabulary, some of the things that we're just going to be throwing around, I'm showing you here the first row transition metals. The first row transition metal starts with D3. Okay, so scandium, titanium, vanadium, chromium, manganese. You see that here. And I'm showing you the possible oxidation states. That is how many electrons you lose and then what the charge are. So you can see from this table right here that manganese, this chemical right here, can have oxidation state as high as 7 and as low as +2. Okay. Almost all the metals have a common oxidation state of +2. Why? Because remember the electron configuration for these things. The electron configuration for scandium, for example, is 4s2, 3d1. Okay, you remember why the 4s level fills first before the 3d, even though the fourth shell is further out? I hope you do. That was something that you guys covered in 200. Okay, it has to do with the fact that the s orbital can penetrate into the nucleus more efficiently than the 3d. In fact, there's a node for the d orbitals in the nucleus, so it can't ever penetrate into the nucleus. The fact that the s orbital can means that it can be stabilized, and so that orbital gets filled before the 3d. Even though it expands further out, it can also be more stable because the s electrons in the fourth shell can actually be near the nucleus where the protons are found. So hopefully you guys remember that from Chemistry 200. If not, you need to go back to that chapter and kind of familiarize yourself with those concepts. Okay. Anyway, the reason why all of these will have +2 in terms of its common oxidation state is because these will be removed first when you ionize these elements. Why is it removed first? Because it's in the fourth shell. The fourth shell extends further out than the third shell. And so they're going to be ionized first. Okay, look at copper, however. Copper has a +1. Why is it +1? Hopefully you guys remember that the electron configuration for copper is actually 4s1, 3d10. Okay, if you don't remember that, then make sure you go review that. Because it's 4s1, 3d10, this electron can be ionized the d orbital is completely full, it gives it added stability. That's why copper has a +1 oxidation state. Okay. Anyway, you need to review that because these are things that are going to be taken for granted when we start talking about these elements. Here is the periodic table, and it shows you their size. Why is their size important? Because remember, the bigger the atom, the further out the electrons are found, and the further out the electrons are found, that is their valence electrons, the more easily they can be removed. They have lower ionization energy, okay? And so you need to understand some of these periodic trend in terms of atomic radii. And so what you see here is that the size actually decrease going from left to right. Why does it decrease going from left to right? Because something called Z effective. Hopefully you guys are remembering all of these terms that I'm throwing out, because you guys learned that again in Chem 200. Let me stop this real quick because I don't want to show that yet. Okay. So Z effective has to do with how the valence electrons are attracted to the nucleus of an atom. It's the effective nuclear charge, okay? And Z effective increases going from left to right in the periodic table. Why? Because the electrons are all going to be in the same outer shell, but now the number of protons increase. Yeah, the number of electrons increase as well, so it causes electron-electron repulsion, but the fact is these electrons in the valence shell sees a greater nuclear charge in the center. And so it causes that electron cloud to collapse. And that's why the electron size, the radius, starts to decrease going across the periodic table, okay? In the transition metal, it goes down and then it goes back up. And that's just the way the d orbitals fill, okay? I want to point out something more closely. Let me see if I can show you this trend. Let me go ahead and do this. I'm going to switch to my computer because in my iPad the volume doesn't quite work. So let me go ahead and do this. Okay, I think this is it. This is it right here. Okay. Let's take a look at this.
It is possible to estimate the radii of atoms in characteristic bonding situations by observing the distances between atoms in molecules. In any given group of the periodic table, for example, group 6A, the atomic radius increases as we move downward. As we move from left to right in any row, the atomic radius generally tends towards smaller values. This occurs because the effective nuclear charge acting on the outermost electrons is increasing. As we proceed across the first long row of the table, in which electrons are being added to the valence shell d orbitals of the metals, we see an overall decrease in radius as a result of increasing effective nuclear charge.
Okay, so again, just a review of the atomic radius here. Let me go ahead and continue here, and let's change this. Take a look at the trend in atomic radius. For the first, this would be scandium, vanadium, chromium, but the second and the third, see how similar these are? And yet you would think going down the periodic table that the lower you are in the periodic table, the bigger the atomic radius. Why? Because you're putting the valence electrons in a shell that is further out. And the question is, why then are the second and third series in the transition metal close in size? And this is known as the lanthanide and actinide contraction. Okay, what happens is that, remember in the periodic table, let me bring a periodic table here. Okay, let me show you that. real quick so you can get an idea of what's going on. When you go from scandium to yttrium, yeah, the shell goes up. The valence shell goes from 1, 2, 3, 4 shell to 5. And so the fifth shell is going to be further out. But when you go from yttrium to lanthanide, yeah, the shell increases as well. But look what happens in lanthanide. You go from barium to lanthium, and then all the way across, you actually have to fill the f orbitals first before you can start filling in the d orbitals. What does that mean? It means that you're actually putting in 14 more protons as you go from barium to hafnium here. 14 more protons in the nucleus will cause the effective nuclear charge to grow immensely and cause those electrons to be pulled in. So that's why um, for these chemicals down here, yttrium and lanthanide, they're similar in size because of the number of protons increased between lanthanum and hafnium versus yttrium and zirconium. That's called the lanthanide contraction. Okay, and that's what causes these things right here to be similar in size. Right here. Okay, right there. Um, So let's move on. Again, a lot of these are fundamentals, hopefully, that you guys have learned in general chemistry. It's just simply a review here. Here are some data for the first row transition metals. When I say first row, I don't mean like the first row hydrogen, helium. I mean the first row in terms of the transition metal. The very row that the transition metal starts filling up is scandium, titanium, vanadium. So this is considered first row transition metals. These are the electron configuration: 4s2, 3d1, 4s2, 3d2. Here chromium is 4s1, 3d5. Do you remember why that's the case? Hopefully you do. It's the same reason copper is 4s1, 3d10. Okay, but here are the electron configuration. Here are the ionization energy. Here are the atomic radius. Okay, one thing that you guys will need to know how to do is give me the electron configuration for transition metals in its ionized form. Let's say I have a chromium plus 3. What's the electron configuration? Well, chromium plus 3 is, chromium's right here. Okay, this is chromium. When I say plus 3, it means that 3 electrons are being removed. So rather than figuring it out based on how you learned it in Chem 200, you would say, okay, argon, the regular electron configuration for chromium would be argon 4s1, 3d5. Okay, it's one of those anomalies. And then if you take away 3 electrons, the electrons in the s orbitals will be removed first. That's your first one. And then 2 electrons in the d orbitals will be removed next. So the electron configuration for chromium plus 3 would be argon, and then it'll be 3d3. Okay, 3d3. Why is it 3d3? Because one of the electrons are removed from the d. 2 electrons are removed from the d, 1 electrons from the s. So that'll be a total of 3 electrons that's being removed from the valence shell. The valence shell would include the 4s orbital and then the 5 in the d orbital. So 6 minus 3 is 3, so it's 3d3. The more easier way to do this, and this is a way that you guys can do without overthinking it, is just think that, okay, it's a plus 3, it's removing 3 electrons. Let's count where chromium is. It's 1, 2, 3, 4, 5, 6. Okay, it's 6. 6 minus 3 is 3, 3d3. What if I ask you, how about manganese 4? What's the number of electrons in the d orbital? Well, manganese is over here. Let's count. 1, 2, 3, 4, 5, 6, 7. 7 minus 4 is 3. It's also going to be 3d3, 3 electrons in the d orbital. Suppose I ask you, okay, how about cobalt plus 3? Cobalt's right here. Okay, let's count from the edge. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 minus 3 is 6. It's a d6. That's the easiest way to do this. Don't over analyze it. Don't try and go, okay, this is the electron configuration. What happened if I remove these and that? Just do it this way and you always get the number of electrons in the d orbital correct. Why is the number of electrons in the d orbital important? Because it's going to give you information about the compound that you have. So the first thing that you need to know is what is the oxidation state of the metal. The second is based on the oxidation state, how many electrons are removed, and based on the number of electrons removed, how many electrons are left in the d orbitals. Remember that the electrons in the s orbitals are always removed first. Why? Because it is in the orbital that extends further out. So it's going to be the electrons that are going to have lower ionization energy than compared to the electrons that are closer to the nucleus. Yes, the s electrons can penetrate into the nucleus. Okay, it's got stability that way, but it also can be further out. And when it's further out, it can be more easily ionized. Okay, so keep that in mind when you're thinking about these things. So it's easy to figure out what the number of d electrons are for any of these. If I say iridium 4, how many electrons in the d orbital? Just count. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 minus 4, 5. It's d5. It's that easy. Don't overthink it. Okay. So again, going back to this idea that we're talking about Lewis acids and Lewis base, we're talking about coordination chemistry, we're talking about ligands that have lone pair electrons that are going to be donating their electrons to the d orbitals of the metal. That's what we're doing. Okay, so Lewis acids, electron acceptors, those are the metals with their d orbitals. Lewis base are electron donors, those are ligands. Okay, these are common ligands. Water, because oxygen has lone pairs electrons. Ammonia, nitrogen has lone pair electrons. Chlorine, it's got chlorine minus has 8 lone pair electrons. Okay, as long as it's got lone pair electrons, it can donate its electrons to the orbitals in a metal. So they can be ligands. So you need to remember the 5d orbitals. Remember the 5d orbitals. Dx squared minus y squared. Those are lobes pointing in the x, y axis. Dz squared, that's the lobe that looks like this right here. It has lobes in the z-axis with a donut in the xy plane. And then the other three, dxy, dxz, dyz, those are lobes that are pointing between the axis. So this right here, see how this is z-axis goes up and down, but the axis in the same plane is x and y. So this is the dxy orbital because the orbitals are pointing in between the x and the y axis. This right here, the orbitals are pointing between the x and the z axis. This is the dxz. This right here, the orbitals are pointing, or the lobes are pointing between the y and the z axis. This is the dyz orbital. Okay, so hopefully you remember that. Anyway, these are the orbitals that are going to accept the lone pair electrons from the ligand. Let me give you some information. Any atoms that are bonded through a network or bonded directly to the metal are confined or are called the coordination sphere. The coordination spheres are those atoms that are somehow linked to the metal. Okay, when you guys did experiment number 6, once you put ethylene diamine and substituted it for water, the ethylene diamine was within the coordination sphere. Depending on what salt you had, some of the waters were within the coordination sphere, some of the waters were outside the coordination sphere, okay, because they weren't directly bonded into the metal. The sulfate That's the counter ion. That was not within the coordination sphere because it wasn't directly bonded. It was attracted to the metal through Coulombic charges because the metal was positively charged and the sulfate was negatively charged. But it wasn't directly bonded through electron sharing. So that's not the coordination sphere. Coordination sphere are only those atoms that are somehow connected directly or indirectly to the metal. Like this right here is ammonia, NH3. Actually, yeah, that right there would be ammonia. And if you have the hydrogen here, it's linked through the nitrogen, and then the nitrogen's connected to the metal. So the hydrogen in ammonia is within the coordination sphere. Ammonia itself is in the coordination sphere. But the counter ions, let's say that this whole chemical is +3, and so you need 3 chlorides to make that whole thing neutral. The chlorides would not be in the coordination sphere because it's going to be just there to neutralize the net charge. So that's what we mean by coordination sphere. Okay. Um, these are some examples of the metal complexes. This right here is a linear geometry. Why is it linear? Well, look at the geometry. It's in a straight line. The metal's in the center, the ligands are flanking it left and right. Okay, that would be a linear geometry. A chemical that had this type of geometry would be this chemical right here. It would be called diamine. That's because ammonia are now called amine. Diamine silver 1. Okay, this right here is the chemical. This right here is either tetrahedral or square planar. Notice that there are 4 ligands attached to the metal. So we say there's a coordination number of 4 because there's 4 bonds coming out of the metal, and a ligand number of 4 because there are 4 unique ligands here. Okay, this would have a coordination number of 2 and a ligand number of 2. This right here is trigonobipyramidal. Okay, it's got a coordination number of 5 because there's 5 bonds coming out of that metal, and a ligand number of 5 because there are 5 ligands. This right here would be a coordination of 5 as well. This is another geometry that has 5 bonds. It's called a square pyramid geometry. This right here would be a trigonobipyramidal. And then octahedral. This is your octahedral geometry. Coordination number of 6, ligand number of 6. The coordination number and the ligand number may not always be the same. Let me just mention that, okay? The coordination number and the ligand number may not always be the same, and let me explain that in the next few slides. But here is other examples, and let me just show you this real quick. No, it's not. Whenever I put, so if you take a look at this right here, that would be examples of compounds that are linear. Okay, these are examples of compounds that are, in this particular case, square planar. Square planar. It's got a coordination number of 4, ligand number 4. Square planar. Look at the geometry. It's a square, and then it's in a plane. This right here is tetrahedral. It's got a coordination number of 4 as well, and these are compounds that would have the tetrahedral. How do you know whether a compound is square planar or tetrahedral? It has to do with the number of electrons in the d orbitals. That's why you need to know that. Remember when I said, okay, what's a copper +2? How many electrons in the d orbital? You guys should be able to figure that out. We'll talk more about this in future slides. This is an octahedral geometry. The reason why it's called an octahedral geometry is because if you look at this and connect all these atoms together, what you have is 8 faces. 4 face on top, 4 face on the bottom. 4 + 4 is 8. That's why it's called an octahedral geometry. This chemical that I'm moving around is also octahedral. Why? Because look at the way the center electrons, the center metal is bonding. It's got 4 in the equatorial plane, 1 on top and 1 on the bottom. But if we rotate this, okay, if we rotate this, then this might be the 4, and this might be on top, and this might be on the bottom. If we rotate this again, Okay, this might be the 4, 1, 2, 3, 4, and this might be on top, and this might be the bottom. The thing about the octahedral geometry is that all sides are identical. All sides are identical. Okay, and examples that might have that octahedral geometry are these right here. In fact, the chemical that you guys synthesize in your lab all had octahedral geometry. Okay, whether it be salt A, salt B, or salt C, or even the starting material, it had octahedral geometry. These are examples of ligand. Now, you might ask yourself, do I need to memorize this? This next quiz is open book. Just get yourself a good list. Okay, but know the common ones. Why do you need to know the common ones? Because your ACS exam might ask you to know the common ones. What are the common ones? Water is a common one. Ammonia is a common one. Okay, and as we get more into this chapter, you'll see certain ligands show up time and time again. The key reason these are ligands is because they have lone pair electrons to donate. All these have lone pair electrons. Okay, and you notice that a lot of these ligands right here come from these acid right here. When you remove the hydrogen from an acid, you only remove the hydrogen, which is simply the proton, and you leave its electron behind. When it was bonded, it had a pair of electrons. Now that pair can be used to donate into a metal. So you can take all these, and if you remove a hydrogen, for example, you get ammonia, ammonium ion. When you remove one of these, you get ammonia. It's got a lone pair electrons to donate. So again, this is just a list that you guys can follow. Here are some examples of coordination compounds. This right here is lead, and this ligand, this is one ligand. Okay, it doesn't look like one ligand, but it's one molecule that is wrapped around the lead. Okay, it's called EDTA. And you might ask yourself, well, haven't I heard that name before? Yes, you have heard that name before because we used it a lot in experiment number 2, I believe. Okay, in the equilibrium lab, EDTA. EDTA is also found in poison control, poison kits. And that's because if a child ever swallowed like lead or mercury or some heavy metal, then EDTA can go into the body, sequester that metal, and make it water soluble because of the OH group in EDTA. Otherwise, if it goes untreated, those metals will adhere to the lipids in the body and slowly secrete over time. That's how lead poisoning works. When you have lead poisoning, the lead gets stuck in the body through the lipids, and then it secretes over time and messes up the central nervous system. So if you have a child eating lead chips, lead paint, okay, usually administer EDTA. That way we can sequester the lead, and then the fact that it's water soluble means that they can urinate it out. Otherwise, it just gets stuck. Here, this is the molecule EDTA itself. Ethylene diamine, you guys know. Ethylene diamine is actually just this chemical, the center chemical right here, the nitrogen, CH2, CH2, and the nitrogen, without this acetate group. This is an acetate group. It's the same acetate group that you find in vinegar, acetic acid. If you replace this bond to the nitrogen with hydrogen, guess what? You have acetic acid. That's why it's called EDTA. It's called ethylene diamine. This is the ethyl part. This CH2, CH2, 2 carbons means it's got a prefix of F. Ethylene diamine, because this is a nitrogen, and a nitrogen, it's like ammonia. So it's got ethylene diamine, and then tetra, meaning 4 acetate. These are the acetate ligands right here, or the acetate fragment. So when you break down the name, you can see how the name gives you information about the structure. Ethylene means that you have 2 carbons in the center. Diamine means you got 2 nitrogen attached to those. And then tetra means 4 acetate group. 1, 2, 3, 4. It looks like a very intimidating molecule, but it really isn't. Okay, that's EDTA. And what happens in nature is that complexation shows up time and time again in living system. For example, in hemoglobin, you've got 4 heme in hemoglobin. Well, that's a coordination where the iron is in the center and it's got these heme groups with the nitrogen bonding to the iron. And then at the very top, where there's an um, empty space, the oxygen can bind to to the iron. That's why if you have iron deficiency, you're going to be anemic because you're not getting enough oxygen in there because there's not enough iron to hold on to that oxygen. Okay. Unfortunately, iron binds better to carbon monoxide than to oxygen molecule. That's why you can easily get carbon monoxide poisoning. The only remedy for carbon monoxide poisoning is by sheer volume. You need to go outside where there's a greater amount of oxygen so that it can displace the carbon monoxide that binds so efficiently to these hemes. But hemoglobin's not the only chemical in our body that is an example of coordination chemistry. You also have vitamin B12 and finger proteins. There's so many. Okay, that's why coordination chemistry also um, has a lot of research in biology. Here are more example: chlorophyll, ferrochrome, oxymyoglobin. These are just a few. Okay, um, and then the question is, well, what drives these chemicals for being formed? And then, I mean, they're so massive, it must be unstable. Okay, they must be able to break down easily. Well, there's actually, it goes back to chapter 18, thermodynamics. Look at this. Look at this reaction. You've got nickel with water. It could easily be cobalt with water, which is experiment number 5. Okay, but now we replace the water with ammonia, and when that happens, it's basically an exchange in the ligands. The water will place the ammonia, okay, and you've got the amine now bonded to the nickel and the waters are kicked out. That has a K formation. Remember, K formation is an equilibrium constant. It tells you the efficiency of that reaction. It has K formation 10 to the 8th, which means that it's pretty favorable in the product direction. The nickel actually has a stronger binding to the ammonia than to water. But take a look at what happens when we replace the ammonia with ethylene diamine. Remember ethylene diamine? Ethylene diamine, this is the ethyl part. And then this is the amine part. It's like ammonia. Except now, one of the hydrogens replaced by this whole group right here. And then there's your lone pair. So this is it right here. That's ethylene diamine. Okay. Uh, because ethylene diamine is what we call it binds the metal at 2 sites. This lone pair and this lone pair can bind the metal. Okay. Then in this structure right here, we have a coordination number of 6, but a ligand number of 3. There's only 3 ethylene diamine that binds us. But look at the thermodynamics. Here we have a total of 4, uh, let's say, molecules. Here we have a total of 7 molecules. 4 going to 7. What does that tell you about entropy? Entropy is increasing. Okay, when you can get more microstates, 7 molecules have more available microstates than 4, then the entropy goes up. So if you take a look at this right here, look at the order of magnitude in the equilibrium constant, 10 to the 18th. Okay, so the driving force for these things to be produced, going back to thermodynamics, is the entropy. Entropy is increasing when you have a more organized, but yet what you see here is that it becomes more molecules in the product. Okay, so that's why these things readily form. Let's talk about nomenclature. because you guys need to learn how to name these things. Okay. And I need to remind you of how you name inorganic salts. Something like CaCl2. You guys know that as calcium chloride. Okay. You know it's calcium chloride, and you don't say calcium dichloride. You only say calcium chloride. You always name the cation first, followed by the anion. Why do you say just calcium chloride? Because you know that calcium is +2. How do you know that? It's in the second pair. It's in the second group. So it's going to have 2 valence electrons. And then chloride's -1. So the only way for this salt to be neutral is if you have 2 chlorides to balance out the +2 of calcium. That's why you only say calcium chloride and never calcium dichloride. Okay. How about something like this? Suppose I have something like copper, um, copper sulfate. Sorry, cobalt sulfate. Okay. How would you name that? Well, you would name this salt cobalt 2 sulfate. Again, you are naming the cation first, followed by the anion. Now, you might ask yourself, well, why did I put a +2 there? Because whereas calcium has a fixed oxidation state, you always know it's +2. It can never waver. Just like um, uh, sodium is always +1. Okay. Well, cobalt can have a +2 or +3 oxidation state. You don't know. So how do you determine from the name what the charge is? You have to write it out in the name. You have to write it as a Roman numeral. And then you know that sulfate is -2. How do you know that? Because you should know polyatomic ions. Okay. So the cobalt 2 sulfate means that the cobalt's a +2, the sulfate's a -2. The formula is going to be COSO4, not CO2SO4. You need to review your inorganic nomenclature, because if you are weak in that, you're going to be weak in the nomenclature here. Okay. So now that we have that out of the way, at least reminding you about the nomenclature that you learn in Chemistry 200, let's take a look at the nomenclature for coordination chemicals. Okay. So I'm going to clear this. First thing that you need to remember is that these things are referred to as complex. Whenever you have a metal with a ligand, they're called complex. It could be a complex ion, or if it's just a complex, it's neutral. Okay. Within the complex, you're going to have ligands, and the ligands are named in alphabetical order. That means amine, AMINE, which is ammonia, comes before aquo, which is water. You don't call water in um, coordination chemistry. You call it aquo or aqua. Okay. Chlorines are called chlorides or chloro. Okay. You'll see that list shortly here. So you name the ligands in alphabetical order before the metal. Okay. Like this right here. You see that? Penta means 5. Amine means NH3. Chloro means Cl. And then cobalt is +3. So how do you put that together? Well, you put that together by writing CO, and then what are the ligands? The amine comes first, NH3, 5, and then the chlorines comes next, okay? And you see how these things are written before the metal? That means it's within the coordination sphere. You put a bracket, and you know there's one chloro because right before the chlorine here, they don't specify it's dichloro or trichloro. If it's just one, you don't even mention the prefix. Okay, so penta means 5, chloro means 1, unless they say dichloro, then you would put 2, and then cobalt. You put the cobalt first in the nomenclature. Then you need to figure out the charge. Cobalt, we said, was +3. Chlorine, you always know is -1. So this whole thing is +2. The whole ion is going to be +2, even though the cobalt's +3. It's a +3, but -1 from the chlorides. That the whole thing is +2. The counter ion to this might be a sulfate. because a sulfate would be a -2, okay, or two nitrates, or even two chlorides. But you need to balance that um, charge of that complex by a counter ions that would be outside the coordination sphere. Okay, so that's how we would write the formula for this particular compound. You'd write it as CO, metal first, ammonia, amine, A before the chlorides, NH3 5 Cl bracket. You have to use that square bracket. And then the charge here tells you it's a +2. If I don't write that charge there, I need to put a counter ion. So let me go ahead and erase this. And let me show you that. Okay. So that's just the example. Ligand, anionic ligand, that is ligands that have charge, ends with an O. That's why when I said chlorines are not chlorides, they're chloro, okay, because they're anionic, they're charged. Amine is just amine. It's not amino because amines are neutral. Water is aqua. It's not aquo because water is neutral, okay? Um, Other examples, Cn minus, cyanide. It's not cyanide, it's cyano. It ends with an O. It ends with an O. Okay. Um, Greek prefixes are used to indicate the number of ligands, di, tri, tetra, penta, hexa, hepta, okay? Except when the name already contains a Greek prefix, like ethylene diamine, ethylene diamine. See how there's a di in the name? Well, if you have two ethylene diamines in the chemical, then you would denote that by putting a bis in front of that, meaning that there are two ethylene diamine ligands in that formula. Tris means that there are three ethylene diamine. You never write ethylene diamine. You're not redundant, okay? Or you don't write triethylene diamine, because the di here means that you already have a Greek prefix in the name. So that's what this rule is about right here, okay? And then um, right here, we have bipyridine. Bipyridine looks like this, by the way. It's basically got, this is a pyridine ring, okay? Pyridine is like a hexagonal molecule in which one of the carbons replaced by a nitrogen. A bipyridine has two of these. And these are the lone pairs that can attack the metal. Okay, so it's called bipyridine, but you can see right here, it's already got a bi within the name. So you can't use, if you got three of these in the compound, you can't use tri-bipyridine. Okay, you have to use the secondary nomenclature, and the secondary nomenclature is tris, tris for tri, bis for bi, tetrakis for tetra. Okay, so I just want to make sure that you understand that. Yes, there's a lot of rules in naming these things, but once you get through the rules, and for those of you who have lab, you have to apply this rule in your next activity in coordination chemistry. So take a look at that while you are doing this exercise. That way you can complete that particular activity as well. And then if the complex is an anion, that is, this whole thing is negatively charged, okay, then the metal has to end in an ATE. Okay, so cobalt is not cobalt anymore like here. It's called cobaltate. Cobaltate. So these are the main rules for naming these things. Let's just look at examples. That's rules for the formula. Cations written before the anion, positive before the negative. The charge of the cation is R balanced by the charge of the anion in order for it to be neutral. If it's not neutral, it's fine. You just know that it's an ion. For the complex ion, neutral ligands are written before the anionic ligands. So you write the neutral before the negative ligands, and that's for writing the formula. So remember, I showed you CO, um, NH3, 5Cl. That's because ammonia is neutral. So it's written first before the chloride, which is anionic. So that's what this rule applies to. Okay. When you name, again, cations before the anions, within the complex ions, the ligands are named in alphabetical order, not neutral followed by anionic, in alphabetical order when you name these things. This is the formula right here. This is the naming down here. Okay. Neutral ligands generally have the molecular name. Okay. Um, Neutral ligands generally have the molecular name. Anionic ligands, you drop the IDE, like chlorides becomes chloro and add O. Okay. This one's kind of sketchy because the molecular name of NH3 is ammonia, but yet you don't call it ammonia, you call it amine. The molecular name of H2O is water, yet you don't call it water, you call it aqua. Okay, so this one needs a little bit more clarification in terms of that. Numerical prefix denoted by the number of particular ligands. Okay, numerical prefix like di, tri, tetra. Oxidation state of the metal ion in Roman numerals, just like in regular inorganic nomenclature. Okay, the anionic complex, the N of the metal name is replaced by ATE. So those are the rules. Let's see how these rules are applied. Let's take a look at this. This right here is chromium. This Cr is chromium. En is ethylene diamine. Okay, break it down that way. F is fluoro. It's called fluoro, not fluoride, because it's a ligand now. And NO3 is nitrate. Okay, so when we name these things, okay, you're going to name the ligands first. And remember, the ligands are named in alphabetical order. So you're going to name E before F. So it's going to be ethylene, diamine, fluoro, and then chromium, and then nitrate. Nitrate's because it's the anion. But there's two ethylene diamines. So the fact that there's two means that we're going to put on this bis prefix. There's two fluoros. So in front of the fluoro, we'll put di fluoro. And the chromium, let's figure out the oxidation state. Ethylene diamines are neutral, fluorines are -1. So 2 here is -2. The nitrate here is -1. -2 and -1, that's -3. The chromium has to be a +3. Okay, it's a +3. So now we can name these things. The name will be bisethylene diamine, 2-ethylene diamine, difluoro, chromium, 3, nitrate. That's the way we would name this right here. Okay, break it down to its parts and then put it together based on the rules that are given. Okay, that's what you need to do. You need to break it down to its parts using what you know on that formula and then put it together. The second one here, let me clear this up real quick. Second one here is potassium. So you're going to write potassium first. I'm going to write potassium over here because that's the cation. Cobalt. Okay. I don't know the charge yet. I'll figure that out last. There's a diamine. NH3 is amine. There's 2 of them. C2O4 is, that acid comes from oxalic acid. H2C2O4 is oxalic acid. C2O4 is the oxalato. Notice I give it a O ending. Oxalato ligand. And there's 2 in front of that. So it's a dioxalato. Okay. And it looks like that's it. So the name for this particular chemical, let's figure out the oxidation state for cobalt. Um, this is a +1. So this whole thing has to be -1. The oxalato is -2 apiece. So that's -4. The oxalato is -2. There's two of them, so it's a -4. Ammonia is neutral. So what plus +1 -4, that's a total of -3. Okay, so the cobalt has to be +3. Has to be +3. When it's +3 and the -4 of the oxalato, that makes it a -1 overall. The whole thing would be -1, and that's balanced by the +1 potassium. There's only one potassium. Otherwise, it would be written as K2. Okay, but you only see K. So the name of this would be potassium, cation, followed by ammonia comes before oxalato, diamine, dioxalato, cobalt 3. Let's take a look at that. Okay, so here we would say that potassium, diamine, dioxalato, cobaltate. I forgot that. Why cobaltate? Because it's the anionic portion of the name. Cobaltate 3. Let's do the last one. This would just be potassium. Gold is not pronounced gold. We use the Latin name aurate. All right. Okay. Arium. Arium is Latin for gold. And the fact that it's an anion means that we have to make this an aurate. Okay. And then cyano, we have tetra, cyano, aurate. And then we need to figure out the oxidation state. So this is +3. That means this whole thing has got to be -3. Then the 4-cyano means that there's -4. The gold is just +1. +1 -4 makes this whole thing -3, which is counterbalanced by the 3 potassium. So the name of this guy would be potassium. Okay, tetracyano R81. Okay, that's how you would name this. Here are the Latin and Greek names for these metals that have been around for a very long time, since antiquity. Okay, so these are the Latin or Greek names that you could use. Notice they end in ATE. So let's do one more here. Okay, let's look at the name and come up with the formula. Hexaamine means that you've got NH3 6 times. Then we have chromium. It's a chromium +3, and then we have a nitrate. Now, it doesn't say how many nitrate. You have to figure that out to make this whole thing neutral. So we've got ammonia is neutral, chromium +3. That means there's got to be 3 nitrates, because the nitrates are the only ones that are going to balance the +3. So this particular formula would be CrNH3 6 times, put a bracket around it, and put NO3 3 times, like that. Okay, that would be the formula. The metal first, followed by the ligands, and there's 6 of them. You put a bracket for the cation, and then the counter ions are the nitrate. Let me just show you that real quick. That would be CrNH3 and then 3 nitrates. Let's take a look at this next one. There's 2 chlorines, that's dichloro. There's 2 ethylene diamines. You abbreviate ethylene diamine as EN. There's a platinum, and it's a platinum 4. And then there's a bromide. Okay, how many bromides depends on how to make this whole thing neutral. So let's put this together. The chlorines are -2 because there's 2 of them. The ethylene diamines are neutral. The platinum's 4. So that means that in order to counterbalance this is a +4, you got to have two two bromines here. So it's Br2. So this would be written as PT, remember alphabetical order, C before E, Cl2, En2 bracket Br2. That's the way I would name that. And that's what you would see here. PT, En, oh, sorry. It's when you're writing the formula, it's the neutral before the anionic. When you're naming it, it's in alphabetical order. So the neutral comes first. That's why I put En first before the anionic En2Cl2, and then two bromides. I forgot about that. Let's do the last one. This ethylene diamine zinc. So there's two ethylene diamines here, and then you have a zinc, and the zinc's plus two. And then you've got uh, your counter ion is copper, and it's a copper 2, and you've got 3 iodines or 4 iodines. Okay, so to write this formula, you would write the cation first. This is the cation. That would be Zn En2 bracket, and then the anion would be Cu I4 bracket. The copper is a plus 2. The iodine is a negative 1. This makes this whole thing a negative 2. This whole thing, therefore, has got to be a positive 2. The En are neutral. The zinc's plus 2. It's neutral that way. Let me show you that real quick. That's not copper. That's mercury. I thought I had copper there. I was blinded. That's actually mercury, Hg. But that's the way it is. I got dyslexia. I thought it was copper. Probably because I saw this Cur, but it's mercury. Okay, mercurate. Anyway, you need to practice this so that you can complete your activity.